All right, Calculus 2 students. So what we're going to be looking at today is a real important integration technique that you will use a lot. Okay, it's called integration by parts. So we're going to first of all start off by developing the formula for integration by parts. And it's related to the product rule for differentiation. So to begin with, what we're going to do is let's just write down that we're going to be doing the derivative of two functions u and v. We're going to use u and v as our two functions. So we're going to do the derivative of u of x and multiplied by v of x. Now, we already know that's the product rule, okay? So I'm going to do it like this, okay? We do the derivative of the first u prime of x, and then we just write down the second, and then that's plus the first, and then times the derivative of the second. A lot of times I do that backwards, so it goes like that. Okay, that's just basically your product rule. All right, now what we're going to do is we're going to develop the formula for integration by parts. So what you're going to do is we're going to integrate both sides of this equation. So I'm just going to bring this down and write this as d dx of u of x times v of x. And I'm going to write down the product rule again, u prime of x times v of x plus u of x times v prime of x. And what we are going to do is we're going to integrate both sides of this equation and rearrange this a little bit as we do that. Okay, so first of all, if you do an integral of a derivative, you're undoing that operation, really. So that would be a u of x times a v of x, like that. Okay, and then what we're going to do on this is split this up. So we can do an integral of a sum as the sum of the integrals. So I'm going to write this as integral u prime x times v of x. And need to squeeze in a dx there. And then the second integral, we'll do the integral of ux times v prime of x times dx, like that. So just using sort of a fundamental integral rule there. All right, now what I'm going to do next is we're going to rearrange these terms a little bit. So I'm actually going to do this. I'm just going to bring this down as u of x times v of x. And what I'm going to do is we're going to solve this equation like this. We're going to move this part over here, like that. So we're going to really subtract that integral from both sides. So we'll have minus the integral of u prime of x times v of x dx equals, and then we'll leave this integral where it is. So that will be integral u of x times v prime of x times dx, like that. Okay, now what I'm going to do on this then is I'm going to write this like this. This part right here is going to be, since this is a derivative, we're going to think of that as du. And on this, we're doing a derivative of v, so we're going to write that as dv, like that. Okay? So what we'll end up having then is we could write this as u of x times v of x minus, and I'm just going to write this like this instead. I'll write this as v of x times du, all right? And then what I'll have here is I'll write this as u of x times dv, okay, like that. I'm just really rearranging that right. I didn't really need to do this. I probably shouldn't have even put that dx on there. That's kind of confusing. That's really unnecessary because I've got the derivative in there. That's really du and that's really dv, okay? So it goes like that. So actually what we end up getting is we get this integration by parts formula. So I can write this as, in a shorthand notation, I can just write that as u times v minus the integral of v du is equal to the integral of u dv. So that is the integration by parts formula, so it's derived from working with the product rule. So it's analogous to the product rule in terms of integration then. Okay, so this is a real important formula. This is a formula I won't give students because it's so fundamentally important you just got to remember it. Integral of u dv is equal to the integral of uv minus v du. All right, so we're going to go to the next page and we're going to start crunching out several of these things. And what I wanted to mention on here is when you have products in an integran, that often suggests to you that integration by parts might be a good technique. Now, what you generally always do in an integral is you think about U substitution first, and if you're not seeing anything working there, then parts is another good strategy for you. So the key in doing parts is to choose U, and you choose dv. And what you have to do is think of U as something that's easy to differentiate, and think of dv as something that's easy to integrate. So what I'm going to do on this is I'm actually going to let that be U. And sometimes you'll do this backwards. It takes a little practice and experience to understand this. And this one would probably easily work either way, I think. But it's certainly easier this way. So what I'm going to do on this one is I'm going to go ahead and just choose U to be X. And then what's left over is dv. All right, remember, we're going to integrate dv and we're going to differentiate u. Okay, so that's why I want to make sure I choose something that's real easy to integrate. Okay, so what I do is this. I do the derivative of x. The derivative of x, of course, would just be 1, but then you need to multiply by dx. Okay, so you want to have that notation. So we just write that as dx. To get v, we integrate e to the x dx. Well, that's about as easy as it gets. That's just e to the x. Okay? So that's how that would get put in. That's what you would want to do, is get that set up in integration by parts then. All right, so we're going to write down the formula. So it goes like this. The integral of x e to the x dx, okay, the integration by parts formula is u times v minus the integral of v times du. And it goes like this. We go u times v. So sometimes I like to just kind of draw these arrows. We go that way, and then we go that way. So it goes like this. U times v is going to be x e to the x, and then v du is going to be the integral of e to the x times dx. So u times v minus integral v du. All right, and when we finish this integral up, we'll have the answer. So this one's a real straightforward example. So that's x e to the x. The integral of e to the x is e to the x. It's an indefinite integral, so you got to put on your arbitrary constant, and then that would be the integral like that. Okay, that's a real straightforward example. These things, like anything else, they can be real simple. Sometimes they can be a real mess. All right, so let's go ahead and let's check by doing the derivative. So you always have the power to see if you've done this right or not. So let's just do the derivative of our answer and see if that doesn't take us back to the beginning like we would expect it to if we did this correctly. All right, so this would be a product rule right here. So when I do the product rule, you can do the derivative of the first, which would be 1, times the second. Okay, plus, and then you can write down the first times the derivative of the second, which is e to the x. So we got that. That's product rule. Then the derivative of e to the x is minus e to the x, and then plus 0, of course. All right, and it looks like what happens is that's going to cross out, so you're going to be left with x e to the x. All right, and see, that matches up with what we started with. So that's a good elementary example of integration by parts. So we're going to look at a lot of different situations on here then. Okay, now what I'm going to do on this, I'm going to pause this just for a second and pull something up. Okay, so let's move on to the next thing. Now I wanted to post this. This is sort of a guideline for how you can do integration by parts. So a lot of times textbooks will have this. Our textbook has this in this. Gosh, this thing keeps messing up. Okay, so there's this statement, lipet, okay, lipet if you prefer. This just tells you the order that it's generally good to choose U in. So this would be like the first thing that you would see. So logarithm kind of gets the highest priority for U, inverse trig, polynomials, exponential, and then trig functions like this. So it's kind of like this is how you can prioritize U in these problems then. So if you were looking at this example, see this has a logarithmic function in it. So that's a real high priority. It's real hard to integrate a logarithmic function. In fact, you wouldn't know how to integrate the natural log of x to the third yet. So you would want to start this problem by letting U be ln of x to the third. Okay, and then the dv, don't confuse this with U substitution, dv would be what's left over. So we're going to use that as x squared dx. Okay, now what we're going to do is put this together and just run through the integration by parts formula then. So remember, dv is something you can integrate easily. So it's easy to integrate x squared dx. Okay, so let me zoom on this. Let's go ahead and put this together then. Okay, so at the side, let's do du. So when we do the derivative of the natural logarithm function, it's 1 over the function times the derivative of that function inside by the chain rule. One of the x's would cross out, so that would leave you 3 over x times dx. All right, so we got that. Now we want to just do the integral. All right, so let's do the integral of this. So when we do v is just going to be the integral of x squared dx. You can do that in your head. So that is x to the third over 3. So we're going to write that just as 1/3 x to the third like that. Now we're ready to apply the integration by parts formula then. Okay, so I'll do this work over here at the side and we'll get this put together then. All right, so I'm going to go like this then. So the integral of x squared ln of x to the third dx, the integration by parts formula is u times v minus the integral of v times du. Okay, so we're ready to plug everything in. All right, so u times v would be this times this. So I'm going to have natural logarithm x to the third times 1/3 x to the third minus the integral of v du. So we'd have 1/3 x to the third times 3 over x dx. Okay, like that. All right, and then we'll put this together then. So this, we're just going to write this, I like to write that as 1/3 x to the third ln of x to the third minus the integral, and let's see, over here, we'll just simplify it before we think about integrating. The 3's cross out. One of the x's crosses out, so it looks like that's going to leave you with the integral of x to the second times dx. Okay, now we're ready to finish it up. So we'd have 1/3 x to the third ln of x to the third. And then the integral of x to the second dx, just by power rule, would be x to the third over 3 times dx. Okay, and let's see kind of what we have here. Now we can clean this up a little bit. That's a good answer. You got the plus c. One thing you could do, there's a property of logarithms. I would go ahead and do this when this pops up. So that's 1/3 x to the third times 3 ln of x, using a property of logs. Then we can write this as 1/3 x to the third. Hold on, I do not need a dx there. Come on. Pay attention, professor. Okay, there we go. That's better. So this will cross out, and that would leave me with x to the third ln x minus 1/3 x to the third plus c. Now you could factor out an x to the third if you wanted to. I can't think of any reason necessarily why to do that. So that would be a good answer to the problem. Of course, you could check that by differentiation. Okay? Okay, so let's go on. Let's move to another one here. Now, some of these things are pretty straightforward. Some of them get a little bit more complicated. We'll see that as we go. We'll kind of increase our level of complexity as we go. All right. So again, with this one, U substitution wouldn't get you anywhere on this. Okay. So what I'm going to do here is let's look at this little diagram here for a minute and just kind of refer to this. And it goes like this. This tells you how to look at u. So you have theta. Theta would be a polynomial. And then secant x squared would be trigonometric, like this. So what we're going to do on this one is we're going to look at this. Remember, dv ought to be something that's easy to integrate. Well, what's easy to integrate is the secant squared of theta d theta. Why? Because the integral of secant squared theta is tangent theta. So that's real easy. So we're going to put this together like that then. All right, so the u will just be this part. And then the dv will be this part right here. Okay, now that's kind of contradictory to what this says. So this is a general guideline. But so you don't always go by that. It's just, hey, this should pop out at you as an easy integral to do. Okay, so du is going to be the derivative of theta, which is 1 d theta. Okay, then we have the integral of secant squared theta. That's what v is going to be. So v is just going to be the tangent of theta. All right, so we got everything put together. Now we're ready to roll with integration by parts. All right, so that would be the way to set that one up. Okay, if something jumps out at you as easy to integrate, then that's the way you want to go with it typically. Okay, so moving from here, let's go ahead and get this put together now. So I'd have the integral of theta, secant squared theta d theta. Write down the parts formula, which is u times v minus the integral of v du. Okay, go this way. U times v is going to be theta, tangent theta, minus the integral of v du. Go this way. So that will be the integral of tangent theta times d theta, like that. Okay. Now we have a formula for the integral of a tangent. Now one thing that I recommend students do is try to get pretty good with figuring out this tangent in your head. There is a formula for this, and it basically goes like this. The integral of a tangent is, and this is how I figure this out. It's kind of like this. Remember the sine, the tangent is sine theta over cosine theta. Now you could do a U substitution to figure this out if you want to, but you can kind of do this in your head if you think about this. So if you just put in ln of cosine theta, well, okay, what would be the derivative of ln of cosine theta? The derivative of ln of cosine theta is just 1 over the function times the derivative of the function. So the derivative of cosine theta is sine theta. So see, that's it. I mean, that's how I remember that formula as I do that then. So you don't really have to do U substitution. You want to just try to reason that out in your head. The other thing that pops up a lot of times is the integral of the cotangent of theta d theta. Well, you know a cotangent is a cosine over a sine. So this would end up being ln of sine theta. However, you got to think about how this would work with a negative here. So see, if you did the derivative of this, you would have 1 over sine, like that. And then the derivative of the sine would be the cosine of theta, like that. Okay? And I think I missed something on this when I was doing this right here. When I do the derivative of ln of cosine, that would be 1 over cosine. The derivative of cosine is negative sine theta. So actually what you would end up having there is you'd have to have an extra negative there when you do that then. Okay? So that's how that one gets put together then. Is you can just apply that formula then if you want to, okay? Okay, so now just kind of putting this together, we can go through and just finish up the integration by. Okay, so now we can go ahead and finish this up. So we'd have theta, tangent theta, minus, and then the integral of the tangent is negative ln cosine theta plus c. Okay, like that. So what I'd end up having then is I end up having theta tangent theta plus the natural logarithm of ln of cosine theta plus c should be the answer to that integral then. So integration by parts gives you that then. Okay, if you wanted to do a quick check on this, you'd have to kind of work with this a little bit if you wanted to check this out. This would end up being a product rule, so I'm going to just show you how this would work. So you would have the derivative of the first is 1 times the second, and then write down the first, and then the derivative of the tangent is secant squared theta. Okay, and then what you would end up having here is the derivative of ln cosine would be 1 over cosine times derivative of cosine, like that. And what would happen is you would end up having tan theta plus theta secant squared theta. This right here would be a minus tangent. Okay, so I'd cross out and that would take you back to the beginning. Okay, so that would be the answer to that problem then. All right, so let's move on to the next situation here and kind of see what we're getting into here. What I'm going to do on this problem is we'll go ahead and get this one put together. And there are times when you have to do a U substitution within that integral itself. So the way I'm going to do this one is, and if you look at that Lipit thing again, okay, I'm just going to take a little quick snapshot of this just to refer to. And what happens on this trigonometric is kind of, we have trigonometric functions here. So what you want to think about is something easy to integrate for dv, something easy to differentiate for u. And it takes practice to do this, okay? When I look at this part of the problem right here, that actually is easy to integrate. Okay, you have a sine and a cosine in the same integral. You could do a U substitution on scratch paper to pretty easily figure that out. So what I'm going to do is I'm going to let dv be the sine of x, cosine of x times dx, and then I'm going to let u be x, like that. All right, so we're going to go ahead and just kind of work this stuff out at the side right here. Let's just get all this stuff calculated over here. So if u is x, that would mean that du is just going to be 1 times dx, so we got dx. Something easy to differentiate. Okay, now we're going to do v is going to be the integral of sine x cosine x. Okay, so you could do a u substitution, and sometimes a little practice you can even begin to do these things in your head. So I'm just going to do a u sub on this. So what I'm going to choose to do on this is let u be sine, and the reason is because the derivative of sine is cosine x dx. So this is a real easy way to do this then. So that's u. du will end up being cosine x dx. So we're going to end up with the integral of u du, which is u to the second over 2. And then plugging back in the u, you would end up just getting sine squared x all over 2. All right, so when we do v by integration, we get 1/2 sine squared x like that. So now we're all set up and ready to go. So there's times when over at the side you have to work out that integral for dv. So now we're ready to go ahead and put together our integration by parts formula. Okay, so what we have is the integral of x, sine x cosine of x, dx, that's equal to u times v minus the integral of v times du. All right, so we'll go ahead and put this together. So we do u times v, so that is 1/2 x sine squared x. Integral of v du goes this way, so that will be 1/2 sine squared x times dx. Okay, then we got to work out that integral then. So this is going to be 1/2 x sine squared x. I'm going to bring out the constant. So I have 1/2 integral sine squared x dx. Now, in a Calc 2, a lot of integrals keep showing up over and over again. So one thing that you want to recall, we've seen this happen a lot, so there's an identity for sine squared x, which is 1 minus cosine 2x all over 2. So when you integrate a sine squared, that's the way to do that, is to just rearrange in the form of that identity. So let's keep working on this. I'll bring this down. That's 1/2 x sine squared x minus 1/2, and I'm going to change this to, and I'll just break this up. I'll do integral 1/2 minus 1/2 cosine of 2x dx like that. Okay, another good formula that will show up that you want to be on top of is if you're doing an integral of a cosine of kx dx, that is 1 over k, and then the antiderivative is, the antiderivative is 1 over k sine kx plus c. So that's going to show up a lot too. All right, so you'll get to where it's just automatic to you how to do an integral of either a sine squared x or a cosine squared x. You apply those half angle identities. Okay, so what we're going to have then is just keep moving on. Just bring this down, 1/2 x sine squared x minus 1/2. I'm just going to do, change this like this. Do my antiderivative. And why did it do that? Why? Why? Okay, so we've got this. The antiderivative of 1/2 is 1/2 x. Then this is a constant, so write it down. The antiderivative of cosine of 2x uses formula is 1 over k sine kx plus c. Now we just need to clean this up, multiply everything out, and then we'll have our answer to our integral. So I'm going to bring this down. That's 1/2 x. Oh, come on. OneNote just messes up. Okay, let's try again here and see if this thing's going to work or if it's just going to misbehave. Okay, so I'm going to bring all that crap down. Just do what I tell you to do, please. There we go. 1/2 x, sine squared x comes down. And then I'm just going to multiply this out. So that would be 1/4 x. And then you have a negative negative. A half times a half times a half is an eighth. Sine of 2x plus c, so that should be the final answer to your integral right there then. Okay, all right. So what I'm going to do is I'm going to do one more example on this video, and then the second part of the video is going to be the more advanced examples. So let's go ahead and go to the next page here and take a look at this then. Okay, so this one now we're doing an integral of a inverse trig function. One thing that I had put on here on your handout is it's good to refresh your memory on these derivatives. What shows up a lot in Calc 2 is going to be these three derivative rules right there. They show up a lot. These not so much. So these things, you really want to know these things right here. The inverse sine and cosine have similar derivative rules. The derivative of the cosine begins with c, so I just wanted to remind you of a few tips. If the inverse trig function begins with c, the answer has a negative in it. And then they're very similar, see? So if you know the inverse tangent formula, then the inverse cotangent's just the same except it's negative. Same thing with inverse cosecant and inverse secant. All right, so those rules show up enough that you want to know that. And then here's your hyperbolic as well on there. So really when I see this problem right here, we're going to have to do this by integration by parts. And what we know is the derivative of the inverse sine is this. All right, so let's go ahead and get this set up then. So we need to pick u, and we need to pick dv. Okay, so u is something easy to differentiate. Well, it's easy to differentiate the inverse sine of x. So yeah, let's start that way. We know that's easy to do. Okay, so that would be the u part. And then that leaves us with something that's real easy to integrate, which is dx. So that's about as easy as it gets. Okay, so we're going to do that. And now when we put this together, du, the derivative of an inverse sine, is 1 over square root of 1 minus x squared. And then the integral of dx, of course, is just x, right? Okay, so you have that. So now we're ready to apply the integration by parts formula. So you start that way. Now we're going to go ahead and just do the integration by parts. So we have the integral of inverse sine of x dx. That's going to be equal to u times v minus the integral of v du. So we'll have this u times v x inverse sine x minus the integral of v du, so that will be x times integral 1 over 1 minus x squared dx. Okay, so that's how everything gets put in that formula. And we're probably, when we work this integral out, we're probably going to have to go to scratch paper and do a u sub on that. Okay, so let's write down what we have. We have x inverse sine of x minus the integral of x over 1 minus x squared times dx. So now what we have to do is we got to really just think, okay, we need to work this thing out kind of at the side here. So that looks like a real good U substitution integral. So I'm just going to do this on the side. Okay, so let's think about how we would do this integral by U substitution. Okay, so I'm going to say let u be what's under the radical, 1 minus x squared, and then du is going to be the derivative of that, which is negative 2x times dx. Then you can divide both sides by negative 1/2 to get negative 1/2 du is equal to x dx. Okay, so then we're ready to put this together now, so our u integral would just be x dx becomes negative 1/2 du. Okay, and then we would have the square root of u. So that would just be negative 1/2 integral of u to the negative 1/2 du. So that's negative 1/2, and then that'll be u to the negative 1/2 plus 2/2 all over 1/2. So that's negative 1/2 times 2, u to the 1/2. 2's cross out, so it looks like you're left with negative square root of u. So that would be negative square root of 1 minus x squared. All right, so that's what we get. So that's what that is. So again, you got to kind of go over at the side of your paper sometimes and work stuff out. Now we're ready to put this all together. So just coming back here, we have x inverse sine x minus the answer to that integral is negative square root of 1 minus x squared plus c. So that's x inverse sine x plus square root of 1 minus x squared plus c. All right, and that would be the solution to that problem. That's one more last example. So what I've given you so far in this part of the video is examples of what I consider the more straightforward integration by parts. So I'm going to close this video here and post this. And then the second part will be things like where we have to integrate by parts more than once and some more interesting examples. All right, so thanks for watching. Good luck on your integration by parts.